All right, welcome back. Let's discuss section 11.2 WebAssign. We're talking infinite series here. So we are introducing ourselves to the fundamental object of study in this course for the remainder of it. And yeah, there's no better way to acclimate ourselves to this than through practice. And may the record show, like sometimes these WebAssign exercises are not that great in terms of assessing through the questions that they're asking of how much you know. And so being doubly diligent to go through the process of each of these will be particularly important. That being said, let's take a look. Oh, is it freezing up on me again? Can we not do this? Why is it doing this? Okay, anyways. What is the difference between a sequence and a series? Okay, a sequence is just a list of numbers, an ordered list of numbers at that, and a series is a sum of a list of numbers. That's really the difference. So in a series, we're adding things up, and in a sequence, we are not adding things up. We're just looking at the things for what they are. A series is convergent if the sequence of partial sums is a convergent sequence. A series is divergent if it's not convergent. Yeah, that's the nature of that. Right. If we have the ANs here, these ANs approach 6 over 8. However, the sum of the ANs eventually start looking like, now you're adding up 6 over 8 plus 6 over 8 plus 6 over 8. And 6 over 8 ain't big, but when you add 6 over 8 in a bundle of times, infinitely many times at that, you get something that grows without bound. And so we get divergence because the series, the sequence is not divergent, but the list of terms is not 0 as n goes to infinity, right? The terms are approaching 3/4. That's the justification. Determine whether this series is convergent or divergent. Now, how are we going to go about this? This is a telescoping sum. So the first thing we're going to do is we're going to write out the sum of the first, I don't know, 3 or 4 or 5 terms. Write out the first however many terms. You'll see a bunch of cancellation. If you put a dot, 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 and then go out to a term that's of this form with the n and the n plus 1, you will see the 1 over n will cancel, the 1 over n plus 1 will not. Moreover, the very first term in this sum, 1 over square root 4, will not cancel because there's nothing to cancel with it. So when you write out a sum of the first million terms or the first billion terms, you're going to end up with 1 over square root 4, or 1 over 2, minus 1 over square root n plus 1. And as n goes to infinity, that 1 over square root n plus 1 goes to 0, which means the sum of these terms is ultimately just 1 over square root 4, or 1 over 2. This is the way that we do telescoping sums. It's very formal, it's very technical, but damn is it satisfying in terms of what you're able to do, because you're adding up infinitely many numbers, even differences in infinitely many numbers. In general, when you see a difference within your sum, that's sort of a tell that telescoping is coming into play. Now, this one is not obviously a telescoping sum. However, when you write it out as ln n minus ln n plus 1 using your ln rules, now you will see that this telescoping sum will ultimately diverge. When you add up a bunch of the terms, the ln1 term at the beginning does not cancel. That gives you a 0. The other term that doesn't cancel is the minus ln of n plus 1 that is at the end. But that minus ln of n plus 1 does not go to 0 in this case. As n goes to infinity, that minus ln of n plus 1 goes to infinity. So you have 0 minus infinity. Hey, that's not convergent in any way, shape, or form. And so here you get divergence as a telescoping sum. A subtle telescoping sum, but nonetheless a telescoping sum. Geometric series here. So when they tell you you've got a geometric series, what you want to look for is the common ratio that you multiply by to get from one term to the next. And here it looks like minus 11 over 8. Multiply by minus 11 over 8, multiply by minus 11 over 8, multiply by minus 11 over 8. And well, if your common ratio is anything bigger than 1 in absolute value, bigger than or equal to 1 of that, you'll get divergence. And so here you get divergence because minus 11 over 8 is bigger than 1 in absolute value. If minus 11 over 8 was less than 1 in absolute value, then you do the first number divided by 1 over 1 minus that common ratio the first number divided by 1 minus the common ratio to get the result, which is actually what comes up here. Check it out. This is a geometric series. it says geometric series right here, and we multiply by 4/5, and multiply by 4/5, and multiply by 4/5. Now here, 4/5 is not greater than or equal to 1 in absolute value, which means we will get convergence. And what will we converge to? A over 1 minus r, where a is the first number, 5 in this case, 1 minus r, where r is the common ratio 4/5. So here we'd have 5 over 1 minus 4/5. You got to do some fraction arithmetic. You got to keep change flip, but so be it. You are adding up infinitely many numbers. That is amazing. Okay, next, here's a geometric series. 0.73 is a number that is less than 1 in absolute value. So we necessarily will converge here because each subsequent term just has an additional multiple of 0.73. What do we need to do to determine what this series converges to? We need to take the first number in the series, plug in n equals 1, see what you get. I think you get 15. And you're going to take that 15 and divide it by 1 minus r, where r is 0.73. r is the common ratio, the number that you multiply by to get to the next term. So 15 over 1 minus 0.73. You'll probably need to use a calculator for this, but whatever, you get convergence, which is pretty cool. Okay, now consider the following geometric series. We have 2 over, does that say n to the, oh no, pi to the n. Pi to the n. Pi is just a number, people. Pi is 3.14-ish. And so here you're multiplying by 1 divided by 3.14 to get to the next number. And 1 divided by 3.14 is definitely less than 1. So we would get convergence. How would we converge? What would we converge to? Well, the common ratio, first off, is 1 over pi. But now what would we converge to? We have to plug in n equals 1 to determine what the first term was. In this case, I believe it would be 2 over pi. And then we have to divide by 1 over 1 minus the common ratio. The common ratio is 1 over pi. Boy, that's a lot of fractions. But when we go through all of the arithmetic, we have just added up infinitely many numbers, which is amazing. Okay, number 9. Is this going to be geometric? A half, a third, a fourth. Oh, this is not geometric, but check it out. If you divide the 1/7 away, you'll get a half, or excuse me, a 1 plus a half plus a third plus a fourth plus a fifth. That is the harmonic series. This is one of the most important series to have in your mind's eye, despite the fact that the terms of this series are getting smaller and smaller and smaller. The sum of the terms of this series is growing without bound. You should be demonstrating this in your class, and this is something, if it hasn't stuck yet, make a note of this. This exercise is one you need to know, and you need to know this as a foundational example, because this example demonstrates a weird fact about series that is somewhat counterintuitive, no doubt. Okay, next one. Hey, look at those terms, equal heavy. Those terms go to 1, but since we're adding those terms, it's like +1, +1, +1, +1. There's divergence occurring there. Here's an example where WebAssign kind of sucks at, testing the result here. They should be cueing you to be like, hey, what's the limit of the terms? The limit of the terms is 1. Since the limit of the terms is 1, what does that mean for the value of the resulting series? Well, you're essentially doing +1, +1, +1, +1, which is growing without bound. Yeah, that type of stuff, important. What about here? Here, we have 8 plus e to the minus n, which if we got rid of the 8, right, just set the 8 aside, because all we care about is convergence or divergence here. We don't care what this converges to. We just care whether we do converge or not. Set the 8 aside, the 1 over e to the minus n is going to be necessarily bigger than the 1 over 8 plus e to the minus n, because if you shrink the denominator, you increase the value of the fraction. And so what we can do, though, is the 1 over e to the minus n, hey, that's just a geometric series with a common ratio of 1 over e. And since that converges, then the series whose terms are necessarily less will also converge. This relates to monotone convergence, because we will essentially bound the sum of some collection of terms by whatever the sum of the 1 over e to the minus n's are, which means the 1 over 8 plus e to the minus n's will have to converge. This is a great demonstration of comparison to demonstrate this. Write the following proposed calculations. Where are we wrong here? identify the errors. I'll let you work with this yourself. This is a little bit bizarre. But take it one step at a time. I think there's going to be an issue somewhere down here at the bottom because we're adding different numbers. So something has to go haywire here. And the fact that we're adding different numbers means that we're manipulating this series in a way that is not accurate. So there's got to be at least one error here. Yeah, read through that one carefully. Okay, what about this? Okay, here's a nice property of series, or rather a nice non-property of series, right? If the ANs converge to A and the BNs converge to B, then if you added the ANs to the BNs, you'd get A plus B. But if you multiply, who the hell knows, right? I mean, the A's could be getting very big, and the B's could be in such a way where whenever you multiply, you no longer get convergence, and let alone converging to A times B. That's a little bit ridiculous, because multiplication doesn't work this way, right? If you take the ANs times the BNs, you'd have a FOIL nightmare to write out A1 plus A2 plus A3 times B1 plus B2 plus B3. You'd have to FOIL like a crazy person, and it does not come out just like this, let me assure you. Right, is this statement true or false? This statement is true, because, and it's, golly, is it counterintuitive. But if you have 9/10 plus 9/10 squared plus 9/10 cubed plus 9/10 to the fourth, double check yourself. That's a geometric series. Run the numbers on that geometric series. You will get 1. You don't have to like it, but that's how it plays out. What about this next one? If the limit of the ANs is 0, then the series is convergent. This is another one. If you do not get this correct, I'm not even going to tell you what the answer is. But I'm going to tell you that previously I paused and said, hey, you need to have this in your mind's eye, one of the previous examples that we looked at. And so if you go back to that previous example that we had that was foundational and you think about it, it will supply you with the foundation of thought for this question. I have seen this question on every single sequence and series quiz and test I have ever seen. It is pervasive, and it is astonishing how many students miss this. It is so counterintuitive to what you would expect a sum to do. Register this in your brain now. Save yourself the torment in the future. The sooner you can understand the correct result of this by going back to an example that demonstrates so nicely what's going on is going to be very, very helpful for your intuition. So nail this one down as fundamentally important and star it, note card it, view it 10 times until you are one with this idea. It's that important. Okay, if a finite number of terms are added to a convergent series, then the new series is still convergent. Sure, you can add a finite number of terms to anything that adds to a finite thing, and you'll still get finite things. Right, if both of these are divergent, then is the sum necessarily divergent? See, this is a problem, right? Because add up 1 plus 1 plus 1 plus 1, and minus 1 plus minus 1 plus minus 1 plus minus 1. When you add their sum, you get 0 plus 0 plus 0 plus 0, not divergent, even though both of them were. So you can get sort of a cancellative effect here, which is essentially why this is a no. And hey, that's that. So I'm going to stop talking. That is an assignment on series, and let's move on to the next one.